The panel would like now to proceed with Dr. Greening's presentation before lunch, and then we'll resume with questions after lunch based on Dr. Greening's presentation. So Dr. Greening, you have 30 minutes. The lights in front of you will glow green as long as you're still within your limit. It'll turn yellow at 5 minutes and then red at the end. Please proceed.
Thank you. I have one little thing I'd like to say based on some questions I was listening to. I'm very surprised that in a room full of PhD chemists and so-called experts that OPG does not know how much zirconium it has in storage, because it's a very simple calculation. One pressure tube weighs 62 kilograms. There are 480 pressure tubes in a reactor. Excuse me. 2 reactors were refurbished. So with my trusty calculator, I arrived at 59.5 tons in storage. And if we go with their 0.1 weight percent of dust, that's 59.5 kilograms of dust. I hope that helps. So I will now proceed with my presentation. We are here today in Kincardine to consider OPG's plan to deal with its problem child, radioactive waste. This problem child was born more than 30 years ago and is becoming more troublesome every day as vast quantities of radioactive waste continue to pile up at OPG's so-called interim storage facility, originally known as the Radioactive Waste Operations Site Number 1, or RWOS-1. What a lot of people don't know was by the year 2000, RWOS-1 was releasing radioactivity into the underlying aquifer, and the site was abandoned. Eventually, the leaking waste was repackaged and moved to an adjacent site, now known as the Western Waste Management Facility, or WWMF. Now, after 30 plus years of prevarication, and mostly, I would claim, for economic reasons, OPG has finally decided what it wants to do with this mountain of accumulated radioactive waste, and that is to bury it, and plenty more that is yet to come, in a deep hole in the ground, euphemistically referred to as a DGR, that is to be excavated adjacent to the present RWOS WWMF location. But OPG is not telling us the real reason for choosing this site, and that is to save the billions of dollars that would have to be spent in moving this pile of radioactive waste en masse to where it really belongs, and that is in a more remote and safer location. But to further save money, OPG has chosen to skimp on the costs of properly characterizing these piles of radioactive waste, perhaps because the analysis of just one sample costs over $1,000. So, in order to minimize these costs, radionuclide inventories of hundreds of tons of waste are being estimated solely on the basis of the analysis of a handful of samples that involve very small quantities of waste and thus can hardly be called analyses that are representative of the inventory. OPG tries to justify not directly analyzing long-lived radioisotopes such as carbon-14 and chlorine-36 in individual waste containers by offering instead a scaling factor approach that uses calculated estimates of radioisotope concentrations as surrogates for real data. In addition, these surrogate data sets are calibrated based on measurements of only one radionuclide, typically the neutron-activated corrosion product cobalt-60. However, and this is very important, there is no theoretical justification for any correlation between carbon-14, chlorine-36, iodine-129, etc., and the cobalt-60 content of a DGR waste container. Indeed, a check of radionuclide inventories reported by OPG shows many other highly questionable scaling factor pairs, such as tritium and cobalt-60. But as reported by ACL, real ion exchange resin samples collected from various storage containers at the WWMF exhibit tritium to cobalt-60 ratios that vary from a low of 0.00017 to a high of 135, which is a factor of almost a million. I would therefore ask OPG a simple question. What scaling factor did it use for tritium in ion exchange resins? And how is that scaling factor determined? Now, for refurbishment waste, OPG relies on a different methodology for inventory estimation, namely neutron activation calculations. However, after I challenged some of the calculated values, OPG acknowledged in a letter dated February the 20th, 2014, that it had indeed miscalculated a number of radionuclide inventories, such as those for tritium, cobalt-60, fission products, and transuranics in pressure tube wastes. In addition, OPG admitted that it had forgotten, yes, forgotten, to consider the neutron activation of garter springs in its calculation of these wastes. In view of these errors in the inventory report, I wrote to SEER and the CNSC to point out that OPG's environmental impact statement with regard to the proposed DGR is now in non-compliance with the requirements of CNSC's regulatory guide G320, because this standard stipulates that, quote, measured values of radionuclide inventories should be used whenever possible in safety assessments, end of quote. But OPG's 2010 inventory report is also non-compliant with regard to SEER's guidelines for an EIS. SEER requires that the environmental impact of a project should be considered as described in a report entitled A Framework for the Application of Precaution in Science-Based Decision-Making About Risk. One of the guiding principles of this framework report is that, quote, available scientific information must be evaluated with emphasis on securing high-quality scientific evidence, end quote. Clearly, when it comes to OPG's EIS, far from evaluating available scientific information or summarizing the existing state of knowledge, OPG simply ignores the considerable amount of directly measured data available for radionuclides in refurbishment wastes, and then, to make matters worse, it makes major errors in calculating these inventories. But now I see that OPG has recently attempted to rewrite the history of this issue. Thus, on May the 5th of this year, OPG issued what is referred to as a frequently asked question, or FAQ sheet, on its DGR, which includes the following question and answer pair. Question, quote, how does OPG account for the discrepancy between Dr. Greening's statements and OPG's submitted inventory report to the Joint Review Panel, end quote. Answer, quote, the estimates used in the pressure tube waste inventory for the 2010 inventory report were based on available information at that time, end quote. Now, this is simply not true. OPG did not use available data, but used fabricated data instead. Worse yet, the discrepancies in question are not due to unavailable data, but are due to mistakes in OPG's calculations. So OPG needs to explain why it ignored real data available from no less than 7 studies carried out between 1990 and 2006, studies that provide a plethora of measured values of radionuclide activities in pressure tubes. And OPG also needs to explain its computational errors. I would now like to consider 2 radionuclides, in particular, chlorine-36 and iodine-129, and I want to consider these in some detail because OPG's response package number 13, submitted to SEER in May of this year, claims that its safety case remains unaffected by my critique of the DGR inventory because I did not specifically mention problems with chlorine-36 and iodine-129. However, this assertion is simply not true because there are major problems with OPG's chlorine-36 and iodine-129 inventories, as I will now explain. OPG is clearly unaware of a study I completed for the Can-Do Owners Group, and it's been issued as an OPG report, and I have it right here. That shows that chlorine-36 is leached from pressure tube ID oxides during reactor operation. Furthermore, the released chlorine-36 accumulates in primary heat transport system ion exchange resin, a process which makes the inventory of chlorine-36 in this waste stream at least 1,000 times higher than OPG's estimate. And research carried out by ACL at the White Shell Laboratories also shows that spent anion exchange resin under normal waste storage conditions undergoes radiolytic and thermal degradation of the quaternary ammonium functional group, leading to gradual loss of radiochlorine and radioiodine. This degradation has a very significant impact on the DGR safety case because OPG erroneously claims that chlorine-36 is first released from a DGR by corrosion of pressure tubes, and this release only becomes significant after about 100,000 years of storage. In addition, OPG asserts that the DGR chlorine-36 release rate never exceeds 50 becquerels per year. Unfortunately, the reality is that more than 1,000 becquerels per year of chlorine-36 will be released from ion exchange resins well before 1,000 years of storage. And in support of this assertion, OPG should consider the fact that the Western Waste Management Facility already exhibits radioiodine emissions of about 10 to the 5 becquerels per year. And sometimes these have been as high as 10 to the 7 becquerels per year. This is iodine-131 being released from the Western Waste Management Facility every year. What does this show? This shows that spent ion exchange resin is unable to retain its complement of radioiodine even for short-term storage, let alone for 1,000 years. And OPG's current radioiodine emissions indicate that there are at least 10 to the 12 becquerels of iodine-131 at the Western Waste Management Facility, yet this radioiodine inventory remains unreported by OPG. So OPG needs to revise its safety case calculations, especially those involving radiohalogen releases from its DGR. And to do this properly, OPG needs to factor in the early contribution to chlorine-36 and iodine-129 emissions from ion exchange resin degradation. But let me emphasize that these are just a few of the questions that could be asked about the proposed DGR inventory. Another issue that certainly deserves mention is found in section 1.3 of the 2010 inventory report, where OPG acknowledges that decommissioning wastes are not included in its inventory estimates. This admission by OPG poses a major problem because decommissioning waste inventories are many times higher than operational and refurbishment waste inventories, yet the latter wastes are the only waste considered by OPG. Thus, by ignoring decommissioning wastes, all of OPG's predicted radionuclide emission rates and radiation doses from its DGR are significantly underestimated. Nevertheless, in spite of these problems, I believe OPG's greatest omission in its attempt to characterize DGR wastes is its failure to consider the chemical properties of many wastes, especially in the event of accidents or acts of sabotage. And it should be noted that OPG itself considers incidents such as an underground fire or an explosion to be credible events. However, OPG's analysis of such events makes two unfounded and dangerously misleading assumptions about the properties of the materials whose safety is being evaluated. These unfounded assumptions are: one, that zirconium alloy wastes are incombustible and essentially inert, and two, that spent ion exchange resin wastes are chemically equivalent to municipal waste such as household garbage. The fact is, both of these assumptions are totally false. Zirconium scrap can indeed burn under certain conditions, which I will get to, and ion exchange resin waste is really nothing like municipal waste. Municipal waste releases mainly carbon dioxide, water vapor on combustion, with small amounts of carbon monoxide, volatile organics such as benzene, and only traces of sulfur or nitrogen compounds. By comparison, ion exchange resins release all of those, plus significant amounts of toxic gases such as ammonia, NO2, trimethylamine, hydrogen sulfide, or SO2, depending on the oxygen supplied to the burning resin. But what OPG fails to recognize is that these wastes should in fact be classified as hazardous wastes, especially in the event of a fire or explosion at the proposed DGR. And this is not simply because of the radioactivity in these wastes, but because of their ignitability, reactivity, and toxicity. More specifically, the pyrophoricity of zirconium waste needs to be considered, and the thermal and radiolytic degradation of ion exchange resins needs to be evaluated. Now, OPG and the CNSC today have suggested that zirconium scrap is not pyrophoric, so please allow me to explain why this is simply not true. Thus, consider the hypothetical malevolent act described as Scenario D, which is in Section 4.3 of OPG's response to EIS 13-514, in which a TNT equivalent of 160 kilograms of an explosive is detonated in close proximity to a pressure tube waste container in a DGR. To analyze the consequences of such an event, OPG uses the following approach. Quote, the consequence of an explosion may be estimated based on experimental data on the fragmentation of metal from a pressure impulse directed inward through the material, end quote. OPG then uses the experimental data taken from the US NRC publication Nuclear Fuel Cycle Facility Accident Analysis Handbook. Unfortunately, OPG fails to recognize that this handbook considers two types of explosive detonation, those involving reactive metals and those involving inert metals. Now, as described by the US Department of Energy handbook, another handbook actually, metals such as magnesium, titanium, zirconium, and uranium are considered to be pyrophoric or spontaneously combustible because of the ease of ignition, and this is important, when they reach a high specific area ratio, which means thin sections or fine particles. Thus, in the context of explosive fragmentation, which is Scenario D, it's fragmentation we're talking about here, and that little movie of them blasting a piece of zirconium with a blowtorch is just silly. I don't talk about that. We're talking about zirconium being exploded and fragmenting. That's Scenario D. Under those circumstances, zirconium is most definitely to be classified as a reactive metal and a pyrophoric metal. Now, that zirconium can show this behavior, and I don't know why the CNSC haven't discovered these reports. They're called spent fuel sabotage tests, and they were carried out at Sandia National Laboratories in the US. These tests were designed to quantify and characterize aerosol particles produced in credible sabotage events involving nuclear waste storage containers. And the particular tests I have copies here if people are interested. Zircaloy-clad fuel was used, and the debris produced by the detonation of a high explosive device placed in contact with the waste container was collected, and the zirconium respirable fraction was measured. High-speed video photography was performed during some of these tests, and what did it show? It showed rapid oxidation, i.e. burning of the zirconium metal. And in addition, zirconium oxidation was indicated by the appreciable amounts of zirconium oxide that was found in the respirable particles that were collected. Now, OPG's pressure calandria tube waste package, and by the way, that's also important. Everyone's forgetting that it's not just pressure tubes in those containers, it's calandria tubes, and calandria tubes are much thinner zircaloy, and I would like OPG to repeat that test with a piece of calandria tubing. That would be closer to reality. But, OPG's pressure tubes do not, pressure tube waste packages do not contain zircaloy fuel cladding, but something quite similar, namely zirconium 2.5% niobium and zircaloy 2 scrap in the form of small coupons and cutting debris derived from the refurbishment volume reduction system. Unfortunately, the analysis of malevolent acts described in OPG's response to EIS 13514 ignores the fact that under the conditions described in scenario D, zirconium will catch fire, and the resulting combustion will impart more than double the energy to the postulated explosion than the energy supplied by the TNT itself. OPG also appears to be unaware that the deadly combination of zirconium and TNT has been used for many years in high-tech weaponry, such as incendiary bombs. Thus, consider, for example, the explosive device described in U.S. patent number 3959041, which was issued in May 1976, and I have a copy of it here if people are interested, and it describes its incendiary device as follows, quote, "The present invention provides incendiary capabilities to a munition by virtue of the incorporation of a relatively small amount of pyrophoric material in the explosive composition of the munition. The term pyrophoric, as used in the present invention, refers to those materials which ignite spontaneously in air when disintegrated into fine particles by detonation of a high explosive. The preferred pyrophoric material employed in the present invention is zirconium metal. Also, the particle size of the zirconium can be varied widely depending on the effects desired. Thus, granules and chunks of zirconium up to ½ an inch thick, strips or sheets about 2 or more inches long can be employed. Upon detonation of the explosive containing the pyrophoric material, there is produced a bright flash which illuminates the surrounding terrain, and the burning zirconium is spread over an area up to 1,000 feet in radius." In light of this information, it appears that OPG and the CNSC are blissfully ignorant of the fact that its supposedly innocuous Scenario D actually describes a very deadly radioactive incendiary bomb. And there can be little doubt that the airborne release and respirable fractions associated with the detonation described in OPG Scenario D would be closer to unity than the values derived from the dispersion of an inert material. It follows that the public dose due to the breaching of a pressure calandria tube waste container by detonation of explosives would be closer to 340 millisieverts rather than the 3 millisieverts predicted by OPG. So in conclusion, it is abundantly clear that OPG has not made an acceptable safety case for its proposed DGR, but on the contrary, has understated the chemical and radiochemical hazards associated with a significant portion of its waste. And overall, OPG has not provided a detailed accounting of the chemical and radiochemical characteristics of the waste it plans to bury in the proposed DGR. Nor, according to its own pronouncements, does OPG intend to precondition or stabilize any of its intermediate level wastes, as is practiced in most countries worldwide that are dealing with similar nuclear waste. Indeed, this disregard for the safe storage of ion exchange resin waste at OPG's DGR was questioned by France and China during the 2009 round of submissions to the Joint Convention on the Safety of Radioactive Waste Management. Nevertheless, in response to these concerns, OPG simply reiterated its position that, quote, the waste acceptance criteria for the DGR do not require a systematic conditioning of the waste. Now, I would say this position illustrates OPG's cavalier attitude to the potential hazards of its nuclear wastes. And speaking of other countries, I would like to briefly consider the U.S. waste disposal site known as the WIPP facility in Carlsbad, New Mexico, which began operating in 1999. On February the 14th of this year, one of the drums stored in room 7 of this facility spontaneously ignited and ruptured, sending clouds of radioactive material to the surface and exposing 22 workers to radiation. The cause of this accident is still under investigation, but the U.S. Department of Energy has announced that the WIPP facility may not be open for up to 3 years. The lessons to be learned from this WIPP event should loom large for OPG and its proposed DGR. But the history of WIPP shows that it is always being an accident waiting to happen. Indeed, the Department of Energy's unusual occurrence reporting system indicates that events such as the discharge of static electricity, spontaneous ignition of pyrophoric materials such as zirconium scrap, reactions involving nitrate-rich materials, and by the way, OPG has gadolinium nitrate absorbed on resins, a whole bunch of gadolinium nitrate absorbed on resins, but that's an aside. But these reactions involving nitrate-rich materials have generated a number of fires, explosions, and incidents of drum overpressurization in the Department of Energy's stored radioactive waste. Ironically, an evaluation of the chemical specifications for waste to be in place in the WIPP facility was carried out in 2002, and the potential for volatile organic compounds to accumulate in the headspace of the waste container was evaluated as part of an accident scenario involving the spontaneous ignition of a drum containing organic waste, placed in room 7 of the WIPP. The resulting official report concluded, quote, the probability of sustained combustion in a partially filled waste room at the WIPP is estimated to be 5.3 times 10 to the minus 6 per year. Now, that would be an underground fire once every 188,679 years. However, as we know, the actual probability of such an incident occurring at the WIPP facility has turned out to be 12,580 times higher than this official prediction, or an underground fire after only 15 years. I would argue that OPG is playing the same kind of guessing game with its so-called predictions of the safety of its proposed underground repository. And as so often is the case, the risks involved in an activity are not recognized before an accident occurs. Only after the fact do the hidden dangers that have always been present become evident. Nuclear waste is dangerous enough. Attempting to permanently store it deep underground only makes it more dangerous. Therefore, I am asking the DGR review panel to simply say to OPG, request denied. And perhaps, if they need to give a reason for the decision, may I suggest this. OPG, the owner and operator of the proposed facility, has failed to properly characterize the waste slated for storage in the facility, and has failed to recognize the chemical hazards that exist in many of the waste packages. Therefore, it has not shown sufficient concern or duty of care with regard to the safety of the proposed facility. For this reason, OPG cannot be entrusted with the stewardship of such a facility. Thank you.
We will now adjourn for lunch, and we'll reconvene at 2 p.m., where we will begin the questions for Dr. Greening.